chosen to be 1. While in the direct synthesis approach, okay, what you do is you compute y by ysp desired. In fact, you don't know it, we design it, ysp desired. And it can be again y by tau cs plus 1, okay. Or if you have a time delay in the system, you put the time delay also, and you equate and figure out what is the value of your, and whatever you write, you would eventually equate to your PID controller structure, which is Kc into 1 plus tau is plus tau ds. And you kind of club the terms which corresponding to the constant part, that would be the Kc of the new controller, and the coefficient of 1 by s would be the the 1 by tau I, and coefficient of s would be tau d. So this is the fundamental difference between both. And one difference, key difference that you would observe when you apply direct synthesis, this may not always yield a PID form. May not. It can yield, but most likely may not yield. May not always yield a PID form. It might hit up at PI, because you have seen in certain cases. So it is safe to say it may be giving you PI or PID. It's up to, so based on the model, it would eventually converge to one of these, and that you would use. Okay, so the same thing kind of applies to IMC also. When you do this filter-based analysis, you might see that sometimes tau d, most likely the absent terms would be tau d. So because the first order system, you would not be able to figure out what is the coefficient of S. So this is not a lacuna. I'm saying PID means you might not eventually get a D term there, but you surely happen to get P and I. And again, the tuning parameter here is the tau C, and there have been some guidelines provided. For instance, tau C can be, tau C, in fact, tau C by theta can be greater than 0.8. This is by experience. And tau C, I think it is greater than 0.1 tau or something. We'll go back and verify. This is one way. There are various options given. So based on practitioners, based on experience, but most widely used, I think this one. So this is all about the what you call model-based controller tuning. So now we will slowly move into tuning based on error criteria, so which I will call as some performance indices. So we will define some performance indices, and based on the performance indices, somebody has done some experiments in the past and documented, and you will use them blindly. So this is the what you call most vulnerable setting, because you are not using anything on your own. This is like, so you might have seen this Paris handbook, heat exchanger design or something. You would see some friction factor chart. These are basically developed by conducting enormous amount of experiments on some fluid, and when you apply your conditions, you would basically blindly take it. You don't do anything, you just blindly take it. But you really don't know if those kind of settings are suitable to you or not, or something. But nevertheless, it's always good to understand it, because people have been documented it after multiple experiments. But as I told, this is the most vulnerable one, because these may not specifically use any of your process information. It is a table. It's basically a lookup, like a logarithm table whatsoever. You calculate, so you compute some error criteria. Okay. Now, based on this error criteria, what they have documented, you just go and fix out the controller setting. So you should be very, very cautious in applying this, but it's good to know what is happening. And the third is field implementation, where you are given a chance to go and do some experiment in the field, and you would do some experiments, collect the data, and come up with the control settings. So we are now going to embark on these two topics now. Any issues at the moment? Are we good? Or again?
Yes, sir.
Okay. So again, as I told, these are based on some performance indicators. So you have to define some performance indicator. One is integral of the squared error, which is generally called as ISE error. One is integral of the absolute error. Then there is a time weight integral of absolute error. These are the three basically widely used three things. And why this is integral is needed, because see, when you apply when you apply controller, when you rather synthesize a controller, and this, let's say this is the YSP, this is time, this, and you are going to plot Y. And when you are going to implement this into the field, you will have to look at the performance starting from 0th time until it reaches steady state, so on and so forth. So every error starting from here is matter. The only way to account this cumulative error by only by means of what you call uh, integration. So So that is the notion of integral. And squared error, of course, if you do a square, the larger error, so for instance, will be penalized higher, and smaller error would be penalized more. So if the error at some point is, let's say, 4, when you do square, it becomes 16. In the same fashion, let's say error is 0.1. When it squares, it becomes 0.1. So what would happen is the the emphasis would be generally given to the larger error compared to the smaller error. So that's why the square comes in. And if you don't want a square, you may take the absolute, but just using error will not be good enough. Why? Because why? Because the error, it can be positive or negative. So when you just take a summation, basically just an integration, which essentially means that its effect would be cancelled by positive or negative. Means square or absolute seems to be better option. Okay, so that is the situation. You may use integral. So I'm saying these are the performance criteria. So when you design a controller and deploy in the field, maybe somebody who is in charge of your section would say how your controller performs. How do you say? You cannot show a graph and see this is not working. Sorry, this is performing like this or not like this. You will say that okay, the ISP of the controller is this, IAE of the controller is this. So they would get an idea. It is performing well or performing bad. And the time weighted absolute error is another option. So time weighted absolute error, it can be time weighted square error also. So this is another option, but we are not. So, so this is time weighted IAE. There can be a time weighted ISP also. What it essentially means. So when the time progresses, right? So initially it's good. You are tolerant for some hiccups because you are starting things, right? So there is some level of possibility, some issue over here. It's okay. You would be tolerant, which essentially means that if this, as long as this time is small, let's say over a 90 minutes batch process, for instance, let's say this is 2 minutes, it is okay, whatever happened is happened. But when the time progresses, right, it's become more critical. You cannot, because most of your products are getting wasted as off spec. So it is also important to look at. So initial times are okay. Like when you start, you don't care, like 1 or 2 minutes, because it is just starting, right? But as you progresses, you are not allowed to make mistakes. Initially, this is the way it works, right? In punishment. So you are okay to have a, so your initial, what you call, mischief would be given away with a warning, but later would be yield a strong punishment. So over that time, so initial time, so when you put a weight over here, so the first would be 1 into E, no problem, no, it is just E only. 2 into E, okay, slightly more. So you have left 1 and going to 2. Let's say it is 100. 100 times E essentially means that, let's say if your E is, error is just 4, but you are multiplying with 100, which essentially means that the weight at this point is 400, which is huge. So what we are trying to say is over the time you are not allowed to make any mistakes. So time weighted absolute error is a very common criteria, which essentially would uh, uh, which essentially used for quality control, endpoint quality control. Endpoint quality control means that when you stop everything, your things should be correct. So over the time, things should improve. And IAE allow so these are the three basic ways. So IAE generally allow larger deviation than ISC because it's an absolute value, not a square one. But ISC might allow longer settling time because you are only looking at the square error. So even though mild variation, it won't care. See, it would take mild variation, as you told, when you take square, it becomes smaller. E become 0.1, E square is 0.01. So you really, in fact, when you really like the final response, you might not see a fine response. You might see there is some variability here. Why? Because this error, when squared, becomes much more smaller. So ITA is like a compromising business. It's later. So initially you are allowed to make mistakes, and later you are not. Okay, so what people have done is they have done a lot of analysis. Based on this, they have documented this particular criteria. How you are getting it? Again, by trial and error, you only need to use this table. Okay, so what is the case over here? Let's say you wanted to design a controller by means of your table. Okay, so for, as you really see, for set point rejection, sorry, set point tracking and disturbance rejection, there are two sets of data, and for PAI and PID, there are two different types of set data. For instance, you wanted to develop a PID controller for set point rejection. So you will have to basically look at these data. So P, I, and D. So now what you have to do is, okay, so design relation is y is equal to a into theta by tau power b, okay, and y is equal to k kc for proportional mode and tau I for integral mode and tau I by d for the derivative mode. For essentially mean that, let's say you want to develop a PI controller and get p where the kc out of it, so it would be k kc equal to, okay, a by theta by tau times b. Theta and tau you will get from your process, okay, and you would take a for p and b and substitute it over here, and you also know your k from the process. You isolate and get your kc back. And when you want to do it for, so let's say later you wanted to do it for your integral term tau I, you will again use the same relation, but it would be tau by tau I on the left hand side. Again, go back and pick these two. And for integral time, which is tau, sorry, derivative time tau d, the left hand side would be tau d by tau, okay, and you will go back and fix the d, sorry, the derivative term. Okay, so now this, so now look at for the set point change, it's all the same, but only thing is the difference is that for the set point change, the integral mode condition is a by beta theta by tau. There is no, so it is not a times, it is a plus b times. So see, for if For set point change, if you want to design a PID controller, for P you will use the same thing, D you will use the same thing, but for I you will use tau by tau I is equal to A plus B times theta by tau. Okay, so now it's a PID controller. You go back and check this. Okay, you substitute the value of A and B over here, tau V over here, theta, everything over here, and get your term back. So this is how, and it's more of a very mechanical way of doing, but people still do, because if you don't have any information, if you need to start something, this also helps, right? Because this is completely independent of any analysis you have. Let's say you are given with a situation and you don't have any, so you are not allowed to do any what you call you are not allowed to do any field experiment. You are not given the model, but they have told, okay, the approximate time constant is this, approximate gain of the process is this, approximate delay of the process is this. So, but these doesn't say help you to understand this is the model structure, because the model can be first order with this, second order with this, third order with this, who knows. So you cannot put either direct synthesis or IMC, or we cannot do any field experiment based approaches, which we are going to see next. So this is a middle ground. Okay, so let's start with this and see whether it works. Okay, so any confusion on this? Are we good? Aranya, Bhavya, Devendra, Harshita, Hemant, Keshav, Shruti,
Yes,
Deep
sir.
and Vishruta. Okay, so this hopefully this okay. So now coming to, okay, so I am just leaving this is you all know, because we have discussed this many times. Kc inversely proportional to what? Just to reduce oscillation, decrease Kc and increase K. We have learned this in the PID controller, so I don't want to put time on that. Okay, so now let me look at, if you really need to do two consecutive things. If you see here, you have set point, you have a controller, disturbance, you have a different PID setting. So you may not be able to. So let's say when you are working in the field, there may be a situation where you have to deal with both the cases. You are also supposed to do a set point change. Okay, so this is your new set point and you are supposed to track it. And meanwhile, some disturbance comes in. So it would tend to oscillate. So you have to kill. So this is the disturbance rejection problem, and this is the which essentially calls the D other or this is the servo problem, which is the S. So what you can do is, so again, so what people tend to do is, if you want to make both ends meet, right? You need to make the error also to be reduced. Also, you need to make the disturbance to be reduced. People tend to use what is known as filtered set point changes. Okay, so I'll tell why this is needed. So here, so it's a minor modification. Okay, what they do is, if you want to really deal with these things together. So, for instance, you need to track the set point, and also you need to make your disturbance rejection together. Integral term will not make a problem. The problem would happen when you have to increase your Kc to track, and during that time, either your Kc would be reacting very fastly, okay. Also, as a result, this derivative time, because derivative is E minus 1. Now, if the error from the previous to this large, these terms would be very strong. So eventually these would push in lot of what you call pressure. So you can use filtered set point, or to avoid this. So filtered set point means set point weighted PI controller. So this is again just a parallel information, and so you may be able to use them in context of controller tuning. So, okay, so now coming to the real case. So the real case in the sense that if you have field case, so let's say forget about the first two cases, you have been allowed to do some field studies. So model is not given to you, okay, and you need a fairly good response, okay. So what you can do, but you have been allowed to do some experiments in the field. So if you are allowed to do some experiments in the field, what you can do is the following. You can do some changes and see how the system responds and come back and do the things. So one of the way to do is as proposed by, so these are algorithmic protocol. Somebody has proposed, you have to go and do it, and based on that result, you do the sum, you do whatever you want. One is a method proposed by Ziegler and Nichols and Tyrus and Leuben. So eventually, the difference here is only in the table. What Ziegler and Nichols proposed and the Tyrus and Leuben proposed is only the difference in the table. So to get, so if you look at this term, so how to get pi, so it says it is 0.45 times some value called kcu and pu times by 1 by 2, and because it is a pi controller, there is no tau d. So it is, another case, it is something function of, so basically it is a function of kcu and pu, which generally called as ultimate gain and period of oscillation. Ultimate period of oscillation. So how to get these two numbers is the key. So if you get these two numbers, it is as simple as that is applying this table. So they are, what they have proposed is performance is proportional to these kind of uh, proportional to this approach. So proportional to Kc and Pu. But how to get this Kc and Pu? They have put forth an algorithmic protocol. Now we will understand what is the algorithmic protocol. Okay, so you are going to do some experiments in the field. Okay, so first of all, before doing the experiment, uh, you will look that the process has reached a steady state. So which essentially means that before you do anything, so it is at a steady state, some steady state, huh? Or it's at least approximately. Why it is saying sometimes it may be mildly drifting. So what it says, it is not really a steady state. It's not a full straight line over here. Okay, but you can say it is partly. So you may assume this is as a straight line, which is a steady state. But if you look at overall, you say that the slope is slowly changing. That is kind of acceptable. Okay, so now what we have to do is eliminate the integral and derivative control. So how to do it? Of course, tau d to make it 0, and it is 1 by tau I, right? So what to put? You cannot put infinity to make it 0. Put a largest value possible. If it is a controller knob, okay, it's between 0 to 100. You make the 100 value, so that the largest value you put, then you eliminate the effect of 1 by tau I. And keep Kc to be a small value. So now you are putting the controller, but it's a small value of Kc by eliminating. This is the most key thing: eliminating the integral and the derivative control. So you then, of course, you increase the set point change. Just do a momentary set point change, and you change your Kc value. Increase the Kc values. It was 0.5 initially. Keep on increasing 0.6, 0.7, until and unless you reach something known as a sustained oscillation of the output, which is typically not really nice, but at this moment you need it. So what would happen in that case? Your output tend to oscillate like this, sustained oscillation. If it is what you call your whatever you measure, you can tend to oscillate with respect to time. Now, what you have done, you're just slightly increased your Kc until you seen this phenomena. So initially it would be like this. It would be die down, then it might. So you would see all of this. So if Kc is higher than the, so you will have to slowly increase. And when you see the sustained oscillation, you stop. And if you increase the if you increase the Kc further, any of these things would happen. So you would come back, reduce, and come to this point. So once you reach that point, the Kc corresponding to the sustained oscillation is basically your Kcu. And once you have this sustained oscillation, you can see, right, how it is varying with respect to time. And this period you calculate. This is your Pu. Is typically called as ultimate gain and ultimate period. And if you have your Kc and Pu, you just use this table. How do you do it? That's why, as I told you, you need to do field experiment. You have to go, interact with the system, switch off your integral and derivative time, then keep your Kc value at the small number and keep on increasing. So the problem is it's a laborious exercise. Why? Because you really exactly need the sustained oscillation. It never can be this or this. This is no oscillation. This is an unstable case. Keep on increasing, and it may be deteriorating the overall performance or even catastrophic to the system. So it's it's tricky, but you can still do. But what you would do is, let's say you start with, let's say, 0.1 kc or even 0.1 kc. You keep it 0.1, 0.15 to maybe until you see some. But again, the problem is laborious, time consuming. Whatever time you do this exercise, what is happening to your system? You are perturbing the system or loading the system, or what essentially means that, let's say you are making $1 million worth products per barrel, all of these products tend to be wasted because you are not doing anything. You are just testing. All your raw material tend to just waste for this experiment. In the lab, it is fine because you are not consuming anything heavily, but in the field, of course not. It's very difficult. But okay, if there is no way what to do, you do it. But again, the issue is you will have to kind of constrain over here. But if you get it, so then this, with thanks to Tyrus and Leuben, they have done, and Ziegler and Nichols, which they have made a very nice table. If you get this Kc and tau I, and they say that this is mostly approximate value. This would give you, because from their experiments and tests and some proofs, they've come up with that this seems to be some rational numbers to work with. And see, and what is the problem here? As I told, it's very consuming, very highly time consuming, and several trials needed. So long experimental run essentially results in poor product quality. And often the problem is this continuous cycling is objectionable. So there is no way out. If you are doing field, you will have to deal with. But you have to be very careful so that it is not going to the unstable character region. So that is like fully upon you. Somebody is given you this process. It's in a controller. You have to be extra guard in such a way that you don't reach into this kind of a situation where things output is keep on exploding. It's just gone off. Correct? So nothing could be done. Okay, so there is a fundamental problem associated with this. Why? Because if you are an open loop unstable, so there are systems which are open loop unstable in the sense that it is, if you don't put a controller to it, it is always unstable. Open loop unstable, very interesting thing. Actually, it is stable only if you put a controller. So when you do this experiment, what is happening? You are anyway, it's an open loop unstable process, and you have to switch off all the controller and living with just a Kc. So it may be not really desirable. And the last is In the other case, one is the instability problem, which is like one extreme, which is like really bad. And look at the other extreme. Let's say you are unable to make this oscillation. For instance, first order systems, second order systems. So the first order and second order systems, right? You may not be able to get this Kc that makes the system sustained oscillating because they are inherently stable to some extent. So one problem is that sometimes if you do, so you will have to kind of deal with these kind of situation. One is one extreme, one is unstable, one is highly stable. So you may be not be able to make the oscillation. One in other case you may have a situation when you start doing some experiment, the things would run out of your hand. So any doubt on this? Anything that is not clear? Am I making sense to you?
Yes, sir.
Hello? Am I audible? Any issues in my voice?
No, sir, no issues.
Okay. So shall we go ahead? Okay, so somebody has proposed a milder alternative to the sustained oscillation case. So what does this milder alternative mean? So, okay, so milder alternative in the sense that you are not, so see, the problem here in this case is two cases. Now, one is highly stable. Highly stable, you may not be impart an oscillation. One is highly unstable. So these are the two extremes. Highly unstable means if you start doing something, things went out of control. So as some people, mainly it is from the Lubin's group. So Lubin was an eminent person from Lehigh University in 90s and 2000s. They have worked significantly and came up with many of these tuning techniques. So these are Ziegler-Nichols is fairly old, maybe 70s, huh? But Tyrus and Lubin could be in 90s to 2000, so like fairly recent, maybe 20 years old, but other maybe 40 years old. 20 to 30, but 20 years maybe. Tyrus and Lubin, possibly 20 years, 20, 25 years. So basically, this particular person who is there, so I think, I don't know whether he still holds a position, but yeah, so he is a professor at Lehigh University. So they have done a lot of work to understood how to tune PID controller in practical sense. So relay auto tuning is also one of their offering from mostly from their group. What they tend to say is, okay, what you really need is just an oscillation. Now, don't do a PID business. So I am going to put a relay. Relay means what? It's an on-off controller. On-off controller, and I'll make artificial uh, what you call oscillation, and with this on-off controller. So this is an on-off, no? It's on for some time, off for some time, on for some time, off for some time. And when you on and off, you would essentially see that the process would be also on and off, because it would be, so the input may be on and off, but your output will not be able to reach this fast, right? Output would be very slow. So let's say it is here, it would just come down and it go up, it comes down, it goes up. For instance, consider AC with a auto cutoff limit, not the inverter one. So when it cuts off, when things are cold, that temperature remains little bit. Then it comes down. When it becomes the low, it restarts. And when it becomes high, when it restarts, okay, it goes up and cuts off. Then it would stay and again cuts off. So basically, if this is input change, your output change will not be like a step change, but it would be a smooth step change. So if this is step, I will cut it. So it would be like a smooth business. I'll make it smooth because it would be the way it is happening. It was expected, response was exactly the same thing. Due to various other aspects, the output would be more smoother than the input. So what Leuben or the and group who has developed this what they call relay auto tuning method mentioned, found that when you change the input uh, to the system, which is the controller output, no, controller output is the input to the process. If the controller output is relay, your process output would be more of an oscillator response rather than a true relay response. Now, what is the disadvantage here? Even it is highly stable, you are perturbing something, switching on and off, you will still get an output response like this. And even if it is highly unstable, you are not perturbing for long to make it unstable. You are going close to the limit, then switching off. So even highly unstable system can tolerate this if you keep the height of the relay this if you keep this height carefully chosen, both stable and unstable system would essentially make an output. So that's what our observation. It was a very smart observation, you see. So the major impediment in employing this field business or this field experiment into the plant was this problem of highly stable system and highly unstable system, how to deal with it. But they found that okay, but again the problem is still not over. If you really need an oscillation, we can do this. Instead of putting Kc tau I, and if you put a controller and change it Kc, but you put a relay inside the system and keep on and off. Your input side, which is the controller output, would be on off, but due to the inherent speed limits, the inherent delay in the system, the output would be, it will not be reflected as a quick on off, but it would be a smooth oscillation. And their key contribution was now, okay, so now you know this PU, A and the relay value 2D. They very nicely come up with this, how to calculate this KCU by these parameters. It's a nice derivation, but due to time constraints, we are not saying here. So he said that this value, by looking at this, what you call D, A, okay, and some properties of sinusoid, you can say that I can back calculate the KCU. So that is the only values remaining, because PU is already available to you. So if you know PU and KCU, you can use either Ziegler-Nichols or Tyrer-Leuben method here. The only requirement is KCU and PU. So this is what you call this relay routing, and advantages. As I mentioned, it just for only one experimental test. You don't have to do anything. You don't have to go and change. And the output can be restricted by the D. So you will be able to make an unstable system to work, be stable, and stable system to be oscillatory. And nobody is forcing you to reach to the stability limit. And disadvantage may be little slow because initial on-offs might not give you a nice, what you call, sustained oscillation, but once you wait for some time, you would get it. But this is not a major disadvantage compared to the key disadvantage of the other methods. I'll stop here and I'll kind of ask for any questions. Any issues here? Sorry. Are you guys okay?
Yes, sir.
Okay, assuming the same, I will move forward. Okay, the second point is step test or process reaction curve. So this has nothing to do with the controller design, but you can do, when you do a step test, you would get a step response and you would be able to develop models out of it. You know how to develop first order or second order models from the step test. Once you have the step test ready, step test done, okay, you can use any of the model based control approaches like IMC or DS, direct synthesis. So step test method would suggest you, okay, use do, so this is like model development. It's not not a controller design, but step test methods would help you to develop a model which further can be used for controller design. Because once the model is ready, then what is the problem? You can use any of the model based control strategies such as IMC and direct synthesis. But there are some disadvantages. First is this an open loop step test. Then because there is no controller when you do a step test, and it's obvious though, and the magnitude of the step might play a, so for instance you can put a step of this size or you can put a step of this size. So if the process has various sensitivity at various steps, so if it is highly sensitive to higher steps, you might not be getting your gain value or what you call the time constant value correctly. Again, the problem here is if it is an open loop unstable process, you cannot do, because when you do a test, it's going to make your system unstable. The same problem that Ziegler-Nichols have. And it may be also, so see, it is also kind of sensitive to some controller calibration error if it is continuous control, because if suppose you are doing an if your controller is not properly calibrated, there's some issue that could pop up. So what I am trying to say is, okay, one approach, this would yield you a model, but if you got the model, go back and do the direct synthesis and what you call uh, the IMC. Okay, so now in couple of some 4 or 5 slides, I would just summarize some of the industrial practice for the design of common control loop. So what are the common control loop mean? It can be flow, temperature, pressure, I think concentration. I think we have flow, level, okay, level also, pressure, temperature, and composition. So flow, okay, I would add level. So these are the 4 important variables that anyway you would do in a process control. This would become some speed, angular velocity, acceleration, etc. if it is a mechanical system. But our system, these are the key variables: flow, level, temperature, pressure, and concentration. And why we need to specifically look them, because as I told, most of the control loop that you see in any refinery or any, they are flow control. And flow controls are generally yield fast response. If you change the flow, it would immediately affect. So generally PI controllers are used for flow control. What is why there is a problem if you use a derivative case? So error is, if there is an error, it is fine, but sometimes it can be measurement noise also when these things work. So this high frequency noise just discourages the use of derivative action, because you may not be able to identify between what is error and what is noise. So PA is the most widely used strategy for flow rates. Okay, liquid level. Liquid level or this is basically the tank level. So what you would do most of the time, either P or PA, but you might tend to use P most of the time. So why? Because see, this integral action is often omitted if there is, so if, so see, this is your tank level, huh? You need to achieve this set point. Okay, if you can at least tolerate 5% of oscillation, which essentially means that level just keep on oscillating 5% of set point, you don't need an integral controller. Even with the P controller itself, it would be able to, you will be able to deal with, because anyway level is a variable, because if you add water to the tank, the meniscus would always keep on oscillating. So there is some inherent oscillation involved. So even if you use PI, you may not be able to fully remove that. So if you want to use, even P controllers are good enough. Again, derivative actions are not used because of the noise. Pressure. Pressure is very similar to level control. Okay. So PI controllers are normally used, and with a small amount of integral control action. And again, as you see, derivative controllers are not needed. Again, the same problem due to the noise related issue. Error can be amplified. So small amount of integral control action means the tau I is R. 1 by tau I should be small. So you have to keep a very high tau I. I come to the temperature. This is one classic case in which you use full PID control. You may not use, so because temperature has a memory, right? Because the current temperature at T is a function of the temperature at T minus 1. So this error, this predictive character would really helpful. So this what you call the anticipatory action. So at if you reach, if the, so if you are at 105 degree, you are moving from previously from some previous temperature which is 100 degrees. So it is more anticipatory. So I'm saying the previous value has some influence in this context. So people tend to use PID or mostly use PID. People don't limit their PI or P over here. And composition. Composition is the most tricky variable to measure. Why? Because there are two things. Huh? One is it would result in a lot of delay, because unlike the temperature or pressure, concentration is a slow variable, and you require some sort of chromatograph kind of a composition measuring instrument to measure this. So what would happen is, if you take a sample now, the result would come a little slow. So that is a problem. And the second is there is a high likelihood of noise because of this high sensitivity. So whatever we have learned, P, PI and PID, they are good for other cases, but in order to measure composition, people tend to use advanced control strategies. If you needed, you may use PID, but it's always recommended to use advanced control strategy, which we are not learning, like model-based, model predictive control, then cascade control, many things. So which possibly you would learn as part of any advanced process control course. Because of these two things, because the delay, because these PID controllers are instantaneously acting. For an error, you correct now. So because of this delay, you would be able to correct for something that has happened much earlier. So it will not be in sync with the current correction. So what would happen as a result? they tends to be slightly ineffective. That's why you need to explicitly use advanced process control strategies for composition, but others are also okay. So with this, I think I have kind of covered, given you an introduction how to do a in-field, or rather, if you are given with a scenario, how to develop a control strategy that maximizes the performance, also assuring the stability. Okay, so the one thing that we have not learned is the optimization. Again, that is part of the advanced process control strategy, because you need to optimize also. Whatever you are doing in the field should be able to will not cost you too much. So I'll stop here. Any questions? Anyone? Request you to please go through it. I don't know whether I have able to communicate with you correctly, but please read it, and whenever we do the tutorial, things become more clearer to you. Okay, some announcements possibly. So next week is of course a holiday week, but and next week is the last week that we'll get, and a week beyond that is your majors. Am I right?
Yes, sir.
So I would really like to finish off everything by next week, so that you will be free in the last week, and the discussions in the class can be mostly regarding your doubts or problem solving or anything. Is that agreeable?
Yes, sir. Great idea.
Okay, so I know Tuesday and Wednesday we have class. I will take it, and I will not be able to complete the portions. There would be like 1/3 of that remaining. So even though Friday is a holiday, Friday I would take the class during the class hours. But again, on record, so whatever that 1/3 was left, you would be able to get. If you are coming, you can attend. Otherwise, it would be available as video. Is that okay?
Sure, sir.
Which essentially means that you will have all the materials available by next week. And the last week, and I think I hope the Tuesday is some quiz, and Thursday, Friday, and any other day, if you need to really discuss any problem, that we will utilize in that fashion. Is this okay to all of you? I hope it is.
Yes, sir. It's okay.
Okay, then any other issues to anyone from anyone? Otherwise, we'll close the session. It's already 11 now. So we'll see you on Tuesday,
So will there be
or
a
rather
tutorial on
Monday
Monday?
for tutorial rather. Yeah.
Yeah.
Okay then. Bye bye. I hope all